As you were saying, at Barco Silex, we are doing electronic design services, and on top of that, we have a complete offering of IP cores. And so the goal here is to explain the concepts and the architectures of our latest designs and how this can bring optimized solutions for cryptography and security solutions. So I will start with a small introduction on market trends and what we mean with best usage of hardware for these IP cores. I will talk a little bit about the solution we propose for AES, the solution we propose for public key, and of course a conclusion. Market trends, obviously, complexity of the designs are increasing. People want to have more functionalities, better performance. They want to have low power solutions. They want to have small solutions, low gate count. And of course, while doing that, keeping the cost under control, reducing the time to market, and the design risks. So taking all of this into account, what we see is that when doing a new design, like a new system on chip, it is based on around 80% of code reuse, so IP cores or building blocks from inside the company. Power consumption is something difficult to grasp because it is highly platform dependent. It depends if you're doing an ASIC, if you're doing an FPGA. When you're doing an ASIC, it depends on the foundry you're working with, on the process you're targeting, and for FPGA, of course, on the family, the speed grade, and so on. What we found is that a solution that provides the lowest gate count to achieve the expected performances and functionality will always give the optimal solution. So the goal is really to achieve a trade-off and optimize the balance between gate count, resource usage, and performances to achieve the lowest power consumption. That's the guidelines for the two examples that we are going to cover. So the first one is AES. So just a quick summary about AES. AES is a symmetric cryptography. This means that the same key is used on both sides, so both on the encoder side and the decoder side. It can provide both encryption and authentication, and it is usually used in streaming applications. AES has a lot of different possible parameters and configuration modes. Of course, it depends if you're doing encryption or decryption. It depends on the cipher mode, which can provide a very different type of functionality and encryption levels. It also depends on the applications. Some applications require low throughput, so some applications require higher throughput. Again, the technology mapping, and all of this makes it very difficult to find the appropriate solution to your application, because you might want to look for a solution that is doing only one mode, for example, a CBC mode, but doing high throughput on a specific platform, and because of all the various possibilities in the offering, it is very difficult to find a solution that will cover your specific case. The idea that we have is to provide a solution that is very flexible, and so I will cover two examples based on two different modes. So the first one is a CCM. So CCM provides both encryption and authentication. So it is actually a combination of two other modes, which are the counter mode and the CBC mode. So the counter mode provides encryption, and the CBC mode provides authentication. So because the message needs to be processed twice, once for encryption and once for authentication, a simple architecture that we could think of is to use two instances of the IP block providing AES, one which would process the CTR mode and one which we would process the CBC mode. So if we look at the figures for such an architecture, we can, so that's typical figures, we can get around 1.4 gigabits per second, and it would use two instances of the IP, each doing 20K gates. What we propose is that by using a pipelined architecture and using an interleave mode, which means that every clock cycle we're just processing one mode or the other, we can actually reduce the gate count by pretty much half the size, while still keeping the same performances. So it's really taking the best usage of hardware, as I was saying. And because of the added pipeline, we can actually go to even higher performances, higher frequency, and get twice as much performances while still getting almost 30% reduced gate count. So the other example is the GCM mode. So that mode also provides encryption and authentication. Here, the payload is still processed in CTR mode, but authentication is computed in Galois field multiplication. So again, the basic architecture would use 2 processing cores, and here a typical solution is actually providing 1.1 gigabits per second and using 35K gates for the cumulated IPs. Here we also take advantage of the pipeline and the interleave functions. Just the difference is that both interleaving are processing CTR modes, and so again we can double the performances while only increasing the resource usage by 10%. Then we can go even further and increase the number of pipelines to improve the performances. And what we find is that we can reach ×4 in performances while only not even adding 50% of the gate count. And again, because of the high level of pipelining, we can go to higher frequency. And when just doubling the gate count, we can actually reach ×7.5 the performances of the basic solution. So the idea with AES that we've developed here is that by providing a flexible and adaptive wrapper, we can easily support all the modes of AES, so actually provide the expected solution. It is easy to maintain and upgrade, so it provides better quality IP. And by spending attention to the interfaces available to the IP core, it will be easier to integrate. So of course, providing AHB or AXI4 or FIFO interfaces. So it's really providing the best balance between gate count and the functionality. Then in terms of scalability, that's what we've seen when we improve the performances of the IP. We can adapt the number of pipeline levels, the width of the data bus, so that we can provide the best balance between gate count and performances. So the bottom line is really that we can size the IP to match the expected performances while not using resources more than needed. So it's really the perfect match between the resource usage and the performances, between the resource usage and the functionality. And that's a bottom line, a basic line for all the IPs. It is always portable, so that you can target either ASIC or FPGA, which is very convenient when we're doing FPGA prototyping before going to ASIC. So that was for the AES. For the public key, so also a quick overview of the public key. There the difference is that you have a key which is public, which doesn't need to be protected, that can be transmitted over the unsecure channel. And if Bob encrypts the message using the public key, only Alice, who has the private key, will be able to decrypt the message. So for example, in a usual cryptographic system, this is what is used to share the key used by the AES, which needs to be common. So the difficulty with the public key algorithm is that it requires a lot of complex arithmetic operations on large numbers. So this induces a lot of data transfer, a lot of computation, and for example, doing a 2048-bit exponentiation in RSA, so that's a typical operation, that requires about 84 millions of 16-bit multiplication. So if you want to do that in software, this is of course going to take a lot of time. It's a significant overhead on the software, so that's the reason why hardware implementations can be very interesting. So as I was saying, if you want to do that in software, a lot of transfer to memories, a lot of computing, so that can quickly generate a significant overhead on the system, which can be an actual problem for a real-time application. A first step to speed up the processing would be to add a hardware coprocessor, but if this one is not fully standalone, it will still require configuration and data management from the main CPU, which will still slow down the system significantly. So the idea here is to move to a smart engine solution, which will bring 100% CPU offload. So what is very important is that is the CPU offload capability of the smart engine. Bottom line, the CPU just provides the operands, sends a go, and waits for the result. And everything is performed by the engine. So it will take care of all the memory transfers, which will be local to the IP. As such, it will free up all the system resources, including the CPU. And since all the data transfers are local, it will consume less power, and it will be easier to use and integrate. Since everything is performed in hardware, and aside the CPU, the performances that you can reach will be higher. And all of this, with the ease of integration, the interfacing, which have been taken care, you can reduce the time to market and the design risk. So that's a small block diagram of the architecture. What is really important to see here is that it is based on a scalable processing unit. It's pretty much an array of DSPs. So that's the core that will take care of all the multiplications we were talking about. And it will really take advantage of the efficiency of the hardware implementation. Then there is a sequencer, microcoded sequencer, which is a very simplified processing unit that will actually take care of the control of the engine. And so it's microcoded. This means that it's easy to upgrade, easy to adapt, easy to configure to the specific need of the application. This is in the microcode that the algorithm itself is implemented. So if there is a need for ECC, we just have the microcode for ECC. If what you need is RSA, it will be the microcode for RSA, or it can be both. It's very convenient, a lot of flexibility to adapt to the specific need. And as I was saying, this is on the bottom here. I hope everybody can see. It's a typical integration of the system. So there is a processor connected on the bus, a local memory, and really the processor just writes the input data, sends a go, everything is handled within the core, not using the bus, not using the CPU, and it just returns an interrupt at the end when the results are available. And in the smallest configuration, all of these just takes less than 30K gates. As I was saying, scalability of the processing unit, just by adapting the number of multipliers integrated in the IP, we can scale the resource usage to match the performance need. And this is really the part that provides the performance and takes advantage of the hardware solution. On the other side, so the microcoded sequencer really takes care of everything. So pre and post processing, the actual algorithm that needs to be done. It will manage all the data transfer. So there is a micro DMA integrated in the engine, which is programmed by the sequencer. And because it's microcoded, it's very flexible, easy to adapt, easy to maintain. So again, we get the most flexibility, able to support all the algorithms, easy to integrate with the interfaces which are adapted, and again providing the best balance between resource usage and functionality. The scalability of the processing unit again provides the best balance between the resource usage and the processing power, and as I was saying, portability, which is key to all our IPs. So to give you some numbers here, what we have is that the architecture of the system provides a fixed level of performances in terms of operations per clock cycle. So if we take a memory clock running at 100 megahertz, we know that, for example, for 1024-bit RSA signature, we know how many operations per second can be performed by the core, because this is really related to the architecture, and just by increasing the number of multipliers, this number will go up. Then we just take a look at the target platform. For example, for an FPGA, we know that the maximum frequency is around 270 megahertz. If we take an ASIC, it will be 500 megahertz, for example. And by just multiplying the two numbers, we get the actual performance of the platform. So here, for example, a high-end FPGA is like a Virtex 6 or Stratix 4. The largest configuration can actually perform 3,000 operations per second. So, as a conclusion, the Smart Engine architecture really provides portability, scalability, and flexibility, as we have seen. What is really key to the integration and to high performance of the system is the 100 CPU offload. Everything is handled as is in the IP, and really helps to the ease and integration. So really, by applying this kind of architecture, we can really get the best usage of the hardware, which means the adapted resource usage to provide the functionality and the performances expected.